Y21 diffraction. Until now, we have studied the interference pattern due to two sources. The Young's experiment is the one to consider the interference of two light waves. They are coherent. Coherent means they have the same kx minus omega t, and the phase difference, nothing. When the two sources generate the coherent light, and when they meet at a screen, only at this point, this central point has an equal distance. Because of the distance difference is 0, they always have the constructive interference. So bright point appears, and depending on the phase difference, this length and this length, in here kx means it is 2 pi x over lambda. So when this one varies, it produces a phase difference in comparison with the starting point. And this phase difference, we usually path length difference, will give the phase difference. And that difference between the two phases will give the interference pattern, depending on the case. If the differences of multiples of wavelength, it becomes constructive interference. And if it is 1/2 and 3/2 and so on, in that case, it has a destructive interference. Today, we study more complicated case, but we remember, we learned how to compute the electric field due to a line charge. We even know how to compute the magnetic field due to a line or circular current. When we compute the electric field or magnetic field due to the distribution of charge or current, we always integrate it. Integration means we sum all of the contributions coming from every partial contribution to the electric field. There is no difference at all to compute the electric field, and then when you know the electric field, you know the electric field energy density, and you even know that electric field, propagating electric field, is always accompanying the magnetic field that is perpendicular to that direction and wave vector and so on. Therefore, we would like to consider the interference of light coming from a finite size hole. The Young's experiment, we assumed these sources were point. Now we make a big hole with aperture width A, and let the plane wave pass through this. Then, according to Huygens principle, just like what we did to compute the electric field, every partial aperture contributes to the electric field. Sure, the Young did not know about the electric field when he consider the experiment and the Huygens leader. So what we want to do is find out the electric field. And if there is a great cancellation, that will be the destructive interference. And if there is enhancement, that will be constructive interference, something like that. So, in short, we would like to divide into tiny pieces of dx, dividing this whole with a, with the dx integrated from 0 to a, to find out the contribution. To simplify our analysis, we would like to let the distance between the perpendicular distance from this big aperture to the screen to be very far. This plot is this figure is an exaggerated one. This hole is very big, but in actual situation, it should be very tiny. I have magnified this hole very large, so you don't have to worry too much about this angle. This angle is very small in reality. For example, we choose this hole to be micrometer, something like that, or much smaller than that, and let it be just 10 meters, something like that. Then this angle is very, very tiny. So we'd like to consider the electric field due to this small aperture within a big aperture of width A. We first consider the distance between this point, origin, and the field point. Then, even though I drew this with a very large angle, it is fine to consider this to be a z-axis, and y-axis and x and y component to be negligible. So this is only expressed in terms of kz. And we have same wavelength, therefore the wave number k is identical to everywhere. And omega is omega over k, that is the speed of light, so it is completely determined. The phase difference is due to the path length difference. We know this is the path length. This should be a right angle, and because the theta is very tiny, this one is also right angle, and this is the path length difference. And if it is a x, then we have angle theta, and this is theta. So sine x sine theta will be, this one will be the x sine theta. That is the path the x sine theta will be the path length difference, and we will divide it by the wavelength to find out the phase difference in comparison with the source coming from the origin. And we integrate over the whole region from 0 to a. So the integrand of the electric field contribution must have this kind of form, and we put this common amplitude. That actually we are not so much interested in the absolute value of the whole amplitude. The relative one is very important to us. We like to divide this one into small pieces, And this should be scale is the same. And in here, if I evaluate the contribution, this should be dimensionless. So it is very convenient to let the scale to be dx over a. Something like when we compute the charge, we charge a distribution along a straight line, then we compute the total charge divided by the length of this wire and integrate over x, something like that. So this one is assumed to be the same, and this scaling factor dx over a, so a represents the length scale of this problem. However, the magnitude itself doesn't matter. As far as we choose a constant value, that's fine. And as I told you, the path length difference is a sine theta. And we'd like to replace this one as a phase. Then what we have to do is multiply 2 pi over lambda. And this one should be substituted in here. And what we want to do is to carry out the definite integral to find the final contribution. Now everything is all set. This is common. We have a phase dependence depending on the position x that ranges from the origin to the maximum value a. High school student can carry out this integral, this sine function. Only the overall factor is complicated. This is a common overall factor. This reciprocal appears in here. Sine becomes cosine. And in here, we have a 0 from 0 to a. The value evaluate a is given in here because indefinite integral of sine is minus cosine. And when we substitute x equals 0, this term disappears. Now, what we have to do is to simplify this cosine something and cosine something plus phase difference. Okay? So this simplification can be made when we make use of this straightforward formula. Until now, we have considered the sum of two contributions. When we consider the sum, we had 2 times cosine, 2 times cosine, half of difference. But in here, we have 2 times sine, half of difference. The argument structure is exactly the same, but in here, it is both sine. That's the difference. So these two factors appears, but as we can see, this is a common factor that oscillates globally, and it is there is no effect on the interference pattern because every contribution has a common value of this. So this one does not contribute to the relative size change due to the interference. The only thing that we have to consider is this strength factor, sine over something. And perhaps you learn in mathematics class without thinking about it. Perhaps you are asked to evaluate this limit as x goes to 0, and in mathematics class you learn that it is 1 by making use of L'Hopital's theorem. However, they have never told you why we have to consider this kind of function. Whatever function you learned in mathematics class is 99% is coming from physics problem. And this is the very physics problem of diffraction pattern give the sinc function you learned in mathematics class. Let's look at this problem more closely. First of all, the brightness of interference pattern depends on the electric field squared. Why? Because we know 1/2 E epsilon 0 E squared is the electric field energy. And according to Maxwell's equations, magnetic field energy is the same as this, right? Although originally we learned like that, but I told you B is a wrong expression. Only if we revive the speed of light to the magnetic field, it is equivalent to the electric field, and the magnitude of this is exactly the same. And time average, trivial time average, is to be multiplied by 1/2. But right now, we are not interested in the absolute value of the overall magnitude of the intensity. We are interested in the relative intensity near that determines the shape of fringe. Finally, at the amplitude level, we have determined the electric field up to an overall vector that determines the intensity of the electric field. And it is completely factorized, and interference pattern appears depending on this function. And this function is called the sinc function. And as x goes to 0, we know the Taylor series expansion of sine, and this higher order piece is negligible as x goes to 0. Another way to evaluate this is by making use of L'Hopital's theorem. Take the derivative, because both of them vanishes, we can take the derivative with respect to x and becomes cosine x, and take the limit x goes to 0, it is 1. And what happens if I increase x to the infinity? It is finite. Absolute value of sine is within this region. However, absolute value of x grows very large as x goes to infinity. Therefore, the shape of this function is something like that, oscillating, but it disappears. Okay? Even though there is a 0, sine x equals 0 at x equals 0, however, this sinc function is 1, exactly 1 at x equals 0. Except that we have zeros of sinc function that is identical to the zeros of sine. So n pi, except for n equals 0, we have all zeros. Haha. By making use of this, we can determine the place where the complete destructive interference appears. When this one is n pi, with n is non-zero, then the point will the electric field completely disappear. That is absolute complete destructive interference. That is here. The brightness, our eye cannot distinguish the electric field oscillation, direction of oscillation. We don't know how, we don't know the polarization. It should be on the x, this is z-axis propagation. Electric field is oscillating either x-axis or y-axis. We don't know. We only know the brightness. That brightness is determined by the square of the electric field, and the square of the electric field is multiplied by some over factor, multiplied by the speed of light, and sum with the magnetic field energy, CB. This is the current density of the brightness. And actually the magnitude of this one is identical to this, and we have to take the time, space or time average. So whatever, this value evaluated at angle theta equals 0, because this is a one sinc function limit as x goes to 0 is 1. This one determines the absolute magnitude at the central maximum. And then after that, what we have to do is that the square, compare the square value. So at the central maximum, we have I0 intensity reference, and we, by taking the ratio at angle theta and the central value, these over a factor contribution completely cancels out. And what we have to do, consider, is the only this factor squared. So sinc function squared is our main concern. And well, now we know everything. The point of a complete disappearance has been computed already. So the remaining piece is straightforward. So repeated explanation for. So let us consider number 4. Electric field squared is proportional to the intensity. And if I divide this one with the value evaluate at theta equals 0, we end up with this expression where the phi is like that. We keep having 1/2. That 1/2, so it's not 2 pi, but pi. So 1/2. The source of 1/2 is this term. In the sum of two sinusoidal functions with a finite phase difference, in that case we had 1/2 phi cosine and duplicative factor 2. In here, in the integral, we have to subtract the contribution of upper limit and lower limit. Because of this negative sign produces the sine instead of cosine. Anyway, even though cosine is replaced with sine, the argument has the same structure. So the phase difference between the two ends, here and there, the phase difference is 2 pi over lambda x sine theta, a sine theta. Because we have to multiply 1/2, this 2 has been disappeared. That's the main reason why I keep multiply 1/2, and this phi represent the phase difference between the two endpoints, 0 and a. Okay, so 2 pi over lambda, and the width, complete width is a sine theta, is the phi, and that phase difference should be divided by factor of 2 due to the calculation integration process. Therefore, we have conditions for local minimum, that is pi over lambda a sine theta, right? That is 1/2 of phi. From this, we can determine local minimum, like that. We can rewrite this in this form. At the central point, because sinc function has a limiting value 1 as x goes to 0, this ratio is exactly 1. What is it? This is a figure depending on the ratio a over lambda. We can find at a over lambda is 1/2, so width is smaller than the wavelength, the shape of the interference pattern. If the angle is small enough, we don't see 0. And actually, there should be some 0 at some point, but finite angle, I don't see any exact 0, vanishing contribution. This kind of case is called exaggerated case, and that is diffraction. The light travels from a single hole, but it is a very tiny hole. Wavelength is lambda, and this hole is about order 1/2 of lambda. Then it does not go straight. Instead, it propagates. Sure, at the end points, the strength decays. However, there is a wide bump appears. This is the consequence of the wave nature of light. Okay. However, if this number increases, if the size of hole increases, what we find is a very sharp peak at the center, and there's a wiggly behavior of the interference pattern. And the width of the interference pattern becomes very dense. If we decrease the hole, magnitude of the size of the hole, then it becomes very wide, and I don't see any wiggly behavior. Okay, this is called diffraction, and there are many straightforward calculations that are mostly tedious, and that are all given in detail in this text. And you will find there is no change in the brightness, the maximum value are almost flat. What's that? It is a slightly different from what we have observed in the previous case, like that, or in the intermediate case, like that. What's that? This is a double slit diffraction pattern. Or in case if we increase the number of slits, you will find more dense behavior and the amplitude won't decay very fast. This is the case of a single slit experiment, and this is for the double slit experiment. And if we increase the number of slits, then it becomes almost flat. That we call diffraction gratings. Okay.